The first question asked about insulin as a water-soluble hormone and to design a system for high blood glucose in the extracellular fluid to cause secretion of insulin. So here's glucose binding to a glucose receptor here, and this person proposed a second messenger from that G-protein coupled receptor, cyclic AMP. Cyclic AMP opens a calcium channel here. Here's the calcium, so calcium in, binds to a binding protein, synaptotagmin, though you don't need to know that, which causes the vesicle to fuse, and here is insulin. So the insulin is pre-made, and that means you don't have to wait for the insulin to be made. Now the real system is actually a little bit different. It doesn't use a G-protein coupled receptor. It's a little unusual, and you do not need to know this, but instead glucose comes in through a glucose transporter, I think it's GLUT4 transporter, which is a passive transporter, goes through mitochondria, which then use it to produce ATP. So it goes through glycolysis and then the citric acid cycle in the mitochondria, and then the ATP actually closes a potassium channel. So normally you'd have potassium leaving. It closes that potassium channel that makes the inside more positive. That opens a voltage-gated calcium channel, and that causes insulin release. You don't need to know that. This one will work just fine, and proposing one that will work is all I'm after here. I want you to have logical answers based upon the toolkit that you know. Here's the second one, and this one is good. I just wanted to point out one thing. So I took off a tiny amount of points for people who had their glucose go through a second messenger pathway and then cause transcription. So you could have glucose activate a second messenger, which then activates a kinase that puts a phosphate on a transcription factor, and here's our phosphorylated transcription factor. And in this case, the person had glucose cause insulin secretion, and then packaging and release. I took off a tiny amount of point because that would give a long delay. It takes at least 30 minutes before you'd be able to release insulin. And so there you'd have at least a 30-minute delay before insulin could start taking glucose out of the blood. And that's potentially dangerous. That would be too slow. So instead, it needs to be the second messenger is causing release of insulin that is already produced, already present. And that's an important point, and I'd want you to be able to realize, oh yeah, that would be awfully slow to measure to take care of something like blood glucose. So a good answer, except for that one piece that I'd like you not to do if you need something fast on the exam. Next was, okay, how might insulin work? And this particular answer, this is somebody who actually knew or looked up how it really does work. So here is insulin coming from the pancreas, gets into the blood, carried in the blood, and so it's going, so blood vessels are leaky for things going in and out. They have gaps. And so here's the insulin getting to the cell. That would be actually going outside of the blood vessel, so the blood vessel should be here. And that activates the second messenger pathway, and that second messenger pathway takes vesicles and those vesicles have the GLUT4 transporters, and I'll just do them as circles here, have the GLUT4 or other transporters in the membrane already. And so the second messenger causes that, here's our transporters, causes that to fuse, and when it fuses with the membrane, it inserts all these GLUT transporters. And these are passive transporters. They just allow glucose in down its concentration gradient. So it inserts them into the membrane, and our cell starts to take up glucose. So to sum up, we have binding, second messenger pathway, and then you could have had your second messenger pathway either activate existing, so if you had existing glucose transporters, you could have had your second messenger pathway activate a kinase, for example, that would then put a phosphate on the transporter, which would allow it to bind glucose, change conformation, and move glucose into the cell. So insulin binding its receptor, 1, activating a second messenger pathway that activates a kinase, that puts a phosphate on a glucose transporter that allows binding and transport. Or the actual way, 1, binding, 2, second messenger, 3, that second messenger cascade causes a vesicle that has the glucose transporters already in it to 4, bind with the membrane, and 5, allow glucose to bind the transporter, and 6, be transported in. I asked about how about regulating the concentration of mercury, which would maybe to get rid of it. We have way too high levels of mercury in our blood. Even the low standards actually are known to be harmful. And so how could you detect mercury in the blood, bind it, and excrete it? There were several ways to do this. This particular person has used a hormone, which is what I had in mind, but you could do it without it. So here's mercury. Mercury binding to a receptor. That receptor has a second messenger pathway. This person had done something which is fine elsewhere. They had shown second messenger pathways and secretion of vesicles, release of vesicles. And so they didn't need to do it again here. Those steps I already knew they knew. So here's our mercury, Hg, and here's our hormone, H1, and here's our hormone going through the blood. Again, blood vessels, capillaries are leaky, so blood gets in, capillaries leaky again. Sorry, hormone gets in, hormone gets out. Hormone here, hormone 1, binds to its receptor, and that activates a second messenger pathway. They have the second messenger binding to a TF. Remember that I'd rather have you have the second messenger binds to a kinase, and then the kinase puts a phosphate on the transcription factor. That's because the second messenger wouldn't stick around long enough to still be present here. So that's what I showed you the first time through, because it's a lot simpler to understand at the beginning, but I'd rather have this be phosphorylated. Anyway, here is our activated transcription factor, and it's making more of two things. Here is a pump that's using ATP to move mercury in, and this one, so here's our more pumps, but this one wouldn't be a pump. This could just be a passive transporter. So more likely, and so this person didn't show ATP here. That's sensible. If you're moving mercury in here, you'd have a higher concentration of mercury in here than elsewhere, and so a passive transporter would move it out. Okay. So that would work. Here's another version. Mercury in the blood binds here, second messenger pathway. Here's the hormone release, and here is another second messenger pathway, activated transcription factor. Here's our ideally phosphorylated transcription factor, and that is doing two things. It's making a mercury transport protein, and it's making the mercury pump. Here's the mercury pump, which is moving mercury out of the extracellular fluid into the mercury. This would be in the kidney, in the lumen of the excretory tubule. So here's the lumen, and here's the wall of the kidney. Pump on one side, transporter on the other. You'd get mercury into the waste, and it would go. So here's the transporter, and here's the pump gene. And cheaper using hormone because there's less energy required than having a whole series of neurons to detect it, and you don't need it to be fast. Neurons can do things in a second or less. Hormones take minimum is about a minute. Typically it's longer than that. So to excrete excess mercury, it's probably not a big deal whether you have to wait minutes or even 15, 20, 30 minutes versus trying to do it in a second. Finally, a hormonal system to control body water. This is the ADH system. And here is a neuron in the brain. this would be an ADH neuron, and this person specified that when the cell is shrinking, in other words, there's not enough body water, then the swelling, this should be shrinking, would open ion channels, and so neuron released. They had a separate ADH secreting cell, which would work. So neurotransmitter released from the neuron, ADH, and then they have ADH going over in here and binding to a cell. And they have two things going on. So if you've got not enough water, you want your ADH to stop the proton pump, so you have less H+, which means you're not going to have as many hydration shells in there, and so that could reduce water loss. And then the second thing it's doing is, in this case, blocking aquaporins, so that water can't be lost into the kidney. And at some locations, this would work. The real system is more complex, and we'll talk about it when we do the kidney. But this person has two things going on. One is you're going to have less acid and less of these other events, so you have less water in the hydration shells. That's going to conserve water, and it'll make this cell eventually stop shrinking, swell back up. The second is, in addition to not allowing the proton pumps to move protons in, you're also not allowing water to come in through aquaporins. So those two mechanisms will reduce the water loss, and that would work.